In this video, we're continuing our discussion of solving systems of linear equations. So we've seen the mathematical background, and we've seen a few methods to solve systems of linear equations, including Cramer's rule and Gaussian elimination. And in this video, we're going to focus on the LU decomposition techniques. So another method that is comparable in efficiency and speed to the Gauss elimination methods is the LU decomposition. It was implied when the Gauss elimination method was introduced that if a linear system of equations AX equals B is such that the matrix A is an upper triangular matrix, then the system can be solved directly using backward substitution. Similarly, if a linear system of equations AX equals B is such that the matrix A is a lower triangular matrix, then the system can be solved directly using forward substitution. So let's look at solving lower triangular systems. We consider the linear system AX equals B defined as here with a lower triangular matrix for A. The system can be solved using forward substitution. So we start with equation 1, and we get x1 directly is equal to 15 over 5, which is equal to 3. Then we move to equation 2, and we can see that x2 is equal to 6 minus 2 times x1, which is 3, all divided by 3. So x2 is equal to 0. And then finally, equation 3, we see that x3 is equal to 2 minus 4 times x1 minus 3 times x2, all divided by 2. So x3 is equal to negative 5. So this process can be generalized by considering the following system here. So this is a lower triangular matrix of n dimension n by n. So the general formula for forward substitution is given as shown here. So xi is equal to 1 over lii times bi minus this sum from j equals 1 to I minus 1 of lij xj. So again, if we consider our general lower triangular matrix and our formula for our xi's, we start with I equals 1. So x1 is equal to b1 over l11, and then x2 is equal to 1 over l22 times b2 minus l21 x1, and then x3 is equal to 1 minus l33 times b3 minus l31 x1 minus l32 x2, where this part here is becoming this sum. And this out to, we work our way down to xn, which is 1 over lnn times bn minus the sum from j goes from 1 to n minus 1 of lnj xj. We can also talk about solving upper triangular systems. So we consider the linear system AX equals B defined as shown here. So in this case, A is an upper triangular matrix, and the system can be solved using backward substitution. So for backward substitution, we start at the bottom. So but with equation 3, x3 is equal to 15 over 5, which means that x3 is equal to 3. Then we move up. Equation 2 is equal to 6 minus 2 times x3, all divided by 3. So x2 is equal to 0. And then equation 1 is equal to 2 minus 4 times x3 minus 3 times x2, all divided by 2. So x1 is equal to negative 5. Again, we can generalize this by considering the system shown here, where we have an n by n upper triangular matrix and associated system of equations. So the general formula for backward substitution is shown here, and this should be familiar from the Gaussian elimination section, where xi is equal to 1 over uii times bi minus the sum from j goes from I plus 1 to n of uij xj. So let's take a look at this. We've got our system and our formula here. So for an upper triangular matrix with backward substitution, we start at the bottom. So xn is equal to bn over unn. And then we proceed to xn minus 1 and continue on. So for example, x3 is equal to 1 over u33 times b3 minus the sum, j goes from I plus 1, so 4 to n of u3j xj. I2 again is shown here, or x2 is shown here, and x1 is shown here. So x1 is 1 over u11 times b1 minus the sums, j goes from 2 to n of uij xj. So let's consider the LU decomposition method to solve systems of linear equations. So we will first introduce the LU decomposition using an example. So consider the system AX equals B shown here. Without explaining how at this point, we will just say that we can decompose the matrix A as the multiplication of two matrices. So A can be written as A is equal to L times U, where L is a lower triangular matrix and U is an upper triangular matrix. So for this particular example, L and U have the forms shown here. And you can verify that LU equals A using the rules of matrix multiplication that we talked about previously. So the linear system of equations can then be written as shown here. So L times U times X is equal to B. So the system can be solved quickly by setting a vector y is equal to u times x, and then setting ly is equal to b. So then we can solve for y using forward substitution, and then subsequently solve for x using backward substitution. So we start with our system ax equals b. We use the LU decomposition to write this as LUX equals b. Then we set ux equals y, and we're left with the system Ly equals b, which can be solved for y using forward substitution because L is a lower triangular matrix. We then plug y into our next expression and solve ux equals y. We can solve this for x using backward substitution because U is an upper triangular matrix. So let's look at this with our example. So we have our system AX equals b. We use the LU decomposition to transform our system into LUX equals b. We then set y is equal to ux and write the system ly equals b. So ly equals b has the form shown here. So we've got our L, our unknown vector y, and our b. We can solve this using forward substitution to find our unknowns y, which for this example is 5, negative 6.5, and negative 20. Then we consider our equation ux equals y, which has the form shown here. So we have our u, our unknown vector x, and the y that we found from the previous step. So now this can be solved using backward substitution, which yields the answer that we're looking for, are x1, x2, and x3. So this example implies that if the matrix A can be decomposed such that A is equal to LU, where L is a lower triangular matrix and U is an upper triangular matrix, then the system can be easily solved using forward and backward substitution. It turns out that such decomposition always exists provided that the rows of the matrix A are properly ordered, and this means that there are no zero pivots during the Gauss elimination step. So let's take a look at the LU decomposition algorithm. There are various algorithms that we can use to find the decomposition LU. And this decomposition is not unique, so there's more than one combination of L and U that can give us A. So here we're just going to look at one of the most common algorithms. In the first step, we use Gauss elimination to turn the matrix A into an upper triangular matrix, which we'll call U. The matrix L then has values 1 on the diagonal entries and the entries Lij that are below the diagonals are the factors that were used to reduce row I using pivot row j during the Gauss elimination step. So Lij is equal to Aij over Ajj. To illustrate the process, let's consider the matrix A given here. So first we want to write the identity matrix on the left and A on the right. So this identity matrix is going to become our L, and A is going to become our U. So first we start with row 1 being our pivot row. So this 2 here is our pivot element, and we want to get rid of the element below that, the 5, as shown here. So the operation we're going to do is row 2 is equal to row 2 minus 5 over 2 times row 1. And this gives us the matrix as shown here. And you can see the factor that we had was 5 over 2. So that means our L21 is equal to 5 over 2. So our L is updated here, and you can see this 5 over 2, or 2.5, is shown here. Next, we want to get rid of the 4 here. So the operation that we do is row 3 is equal to row 3 minus 4 over 2 times row 1. Again, and that gives us the matrix shown here. And our factor is equal to 4 over 2, so that means our L31 is equal to 4 over 2. So that goes here. Next, we want to get rid of, we update our pivot row is row 2, and we want to get rid of this 1 here in row 3. So row 3 is equal to row 3 minus 1 over negative 0.5 times row 2. Gives us the matrix shown here, and we have arrived at our upper triangular matrix U. And you can see our factor here is 1 over negative 0.5, so that becomes our L32, and that ends up right here. And you can see that L is now a lower triangular matrix. So going through this process, we've arrived at both our L and our U. So 2 functions were written in MATLAB to perform this operation. First is called LU factor of A, and then it returns, so the input is a matrix A, and it returns the matrices L and U, just to demonstrate the LU factorization of a matrix A, and it shows printouts of the intermediate steps. So this is posted on eClass. You can take a look at it and run it with various examples of A. The second is called LUAB, and the inputs are the matrix A and the vector B, and the output is the solution X, so it solves the linear system of equations AX equal B, and it uses it calls the LU factor function of A to do this LU decomposition, and then it performs the forward substitution and backward substitution to solve for X. It's also, you can note that MATLAB has a built-in function called LU, where the outputs that you can choose are L, U, and P, and the input is the matrix A. And so it does the same thing. It gives you the L and U that can be combined to give A, but it may not give the same result as the functions that I've provided, as we said, the LU factorization is not unique, so they use different algorithms. So with our matrix A, this is the result of the LU factor code. So you can see we start with the original matrix, and then after, and then what the original L and U are. So L is the identity, and U is just the original matrix. And then after the operations where we have our pivot row is the row 1, we end up with these versions of L and U, and then we move to have pivot row 2, and after those operations, we get the matrices shown here, and this is our final result for our L and our U. So again, you can see that L is a lower triangular matrix and U is an upper triangular matrix. And with this definition, or this algorithm, the diagonal elements of L are 1. And using that same A with this vector B given here, so this system of equations produces the result here when we call LUAB. So again, we can arrive at the same L and U shown here, and then after the forward substitution, we end up with this result, and then after the backward substitution, we end up with our final result, X, shown here. So we can compare the LU decomposition method with some of the other methods that we've talked about. So in comparison to the naive Gauss elimination method, the LU decomposition reduces the computations in the forward elimination step by conducting the forward elimination only on the matrix A, without adding the vector B. However, it adds another step, which is the forward substitution. The advantage of the LU decomposition method is that no manipulations are done on the vector B, so it is good for solving systems where B changes or is not known in advance. So if the matrices L and U are stored, then only substitutions need to be repeated when B changes. So if you use the same A and a bunch of different B's, you can just do the decomposition into L and U once, and then repeat the substitution part of the solution with all of your different B's. So the last thing that we want to introduce here is the Cholesky factorization for positive definite symmetric matrices. So positive definite symmetric matrices appear naturally in many engineering problems. The stiffness matrix of elastic structures are a particular example. So positive definite symmetric matrices have positive eigenvalues, so working on them can be very easy. Also, being symmetric, only half of the off-diagonal components need to be stored, which reduces the computation time significantly. So the Cholesky factorization is a particular type of LU decomposition that can be applied to symmetric matrices. In particular, a positive definite symmetric matrix can be decomposed such that A is equal to L times L transpose, which is also equal to U transpose U. So L is equal to U transpose is a lower triangular matrix, and its transpose, L transpose, which is equal to U, is an upper triangular matrix. So for example, the following symmetric matrix is positive definite because all of its eigenvalues, when we calculate them, are positive. A admits the following decomposition, which we can write as U transpose U. So we have A, and we can write it as this decomposition of U transpose, which is a lower triangular matrix, and U, which is an upper triangular matrix. And you can see that this one is just the transpose of this one. So the procedure to calculate this is shown here. So the diagonal components of U are given by the expression shown here. So this is to calculate our UII, just the diagonal components. The off-diagonal components, the ones only above the diagonal, so for when j is greater than I, are given by the expression shown here. So just j, or U of ij, when j is greater than I. So this gives us, because everything below the diagonal is 0, everything above the diagonal is given by this expression here. So we can call the diagonal component equation 1, and the off-diagonal component equation 2. So how this works is the elements of U can be found by first setting I equals 1, and then iterating over j from 2 to n. And then you set I equals 2, and iterate over j from 3 to n, and so on. So again, let's put our equations here and illustrate this with an example. So consider again our symmetric matrix here. And we want to show how we get the upper triangular matrix U from this. So first we set I equals 1 in equation 1. So plugging in I equals 1, we get U11 is equal to the square root of A11. And as you can see, the sum doesn't appear here because k goes from 1 to I minus 1, and I is equal to 1, so k would go from 1 to 0, so we don't have any part of the sum. So our U11 is just equal to 1, as shown here. Then we iterate from j goes from I plus 1, or so in this case 2, to 3. in equation 2. So U12 is equal to 1 over U11 times A12. And again, you can see the sum does not appear here because, again, we're going from k equals 1 to 0. So the sum doesn't contribute. So our U12 is equal to 3, and that appears in the matrix here. And then we increment our j. So now we're looking for U13, and that is equal to 1 over U11 times A13. And again, the sum doesn't appear because I is still equal to 1. So that gives us our 2. So that completes our first row. So now we increment I and set I equals 2, and we're going to be looking at the second row here. So to find the diagonal component, we look at equation 1. So U22 is equal to the square root of A22 minus U12, which is equal to 2, as shown here. Then we iterate j from 3 to 3 in equation 2. So U23 is equal to 1 over U22 times A23 minus U12 U13, which is equal to 1, as shown here. Then we increment our I again and set I equals 3, and again use equation 1, where U33 is equal to the expression shown here. So now we have 2 elements of our sum coming into play, and this gives us 1, which is our last element here. And then we don't need equation 2 at all, because if we set j is equal to I plus 1, that's equal to 4, which is outside of our matrix. So our final upper triangular matrix is shown here. After factorization of A, the solution of a system of linear equations AX equals B can be solved using the same procedure as described earlier. So we start with our AX equals B. We use the Cholesky factorization to give us our system in this form, U transpose U X equals B. We set Y is equal to UX. So then we look at the system U transpose Y is equal to B, and we solve this for Y using forward substitution. We then look at our system UX equals Y and solve for X using backward substitution. So again, 2 functions were written in MATLAB. The first is called Cholesky, and it takes a matrix A and provides the upper triangular matrix U. So this demonstrates the Cholesky factorization of a matrix, showing printouts of the intermediate steps. The second is called Chol-AB, and it takes the matrix A and the vector B and produces the result X. So it solves the linear system of equations AX equals B. And it uses the function Cholesky to perform the factorization of A. And it's important when you're using these functions that A must be symmetric and positive definite. And it's also, we can note that MATLAB has a built-in function to perform the Cholesky factorization, which is called Chol. And so you just supply it the matrix A, and it will give you the matrix U. And so you can compare that with the Cholesky function that I've posted on eClass. So using our same matrix, this is the result from the first function. So we plug in A and we get U, and it shows the different steps along the way. So this starts with the original matrix, and this is how we end up with row 1, row 2, and row 3, and to arrive at our final result, which is U. Then the same matrix A was used with this system of equations with this vector B to find the values of x1, x2, x3. So this shows the result of the forward substitution method, which gives us the vector y, and then the backward substitution method gives us our vector x. So this is our final result. So all of the methods that we've talked about so far for solving linear systems of equations are in the category of direct methods. So we can just talk a little bit about the advantages and disadvantages of direct methods in general. So the advantages are that the solution is obtained directly by performing the algorithm only once, and that the solution is obtained to the highest possible accuracy, which is machine precision. So there's no error threshold that we're comparing to or anything. It is the solution that we get is the highest possible accuracy. The disadvantages of direct methods are that the number of operations required grows with n to the power of 3 for Gauss elimination or n to the power of 2 for the LU decomposition after the factorization is completed. So this can quickly become very large for realistic engineering problems, which would require a long computational time. The other disadvantage is that memory storage can become an issue because even sparse systems, which have lots of zeros in them, need to be completely stored in memory, since elimination and factorization both result in dense matrices. So this concludes the discussion of direct methods, and next we will look at iterative methods to solve linear systems of equations.